Good morning, guys. Welcome back. This is actually the final lesson of the sequence chapter, and so on this is either Monday or Tuesday when you're watching this. This is the final lesson, and then Wednesday or Thursday you'll get a little review for the chapter. I will put up a little test for this chapter like I did for the last. Some of you guys have actually emailed me about the vectors test. I did officially grade it, so if you want to go in and look at your submission, you should be able to see how you did. I'll also put them in the gradebook soon if they haven't already been updated, and so you'll see. I think most guys are pretty well. It should help most of you. And obviously, if not, again, it won't factor into your grade. So take a look at that, and then again, keep working on this, and we'll go from there. So this again is the final topic. You can see by the title, it's another type of special sum. What we mean by that is, so we found ways to add linear sequences. We call those arithmetic. We found ways to add geometric sequences. We called those, or they were exponential as well. This is how to add together different kinds of polynomials. So we're going to specifically do what about squareds, like quadratics, and then later we'll talk about what about cubics. And you could technically use what we see here to continue climbing as high as you want. Really, there's no limit to what you can do. We just do these two for something to work on, but we really could do any type of power that you want to. So let's dive into it. I actually think these are kind of cool how they end up working out, and we'll see if you agree with me, but I'll show you the whole process as we go. So first things first, let's just kind of explore a little bit. As it says, let's derive the formula, and by doing so we'll just mess around a little bit and see what we come up with. We're going to start by, for the first column here, we'll just figure out what are all the terms of this thing as we lay it out, and then secondly we'll actually start adding them up as we go. So maybe I'll just write it up here first. If you actually wanted to add these together, we're saying start at 1, go until whatever n is. The sum of that many things is what you'll find at the end. And so in this case, 1 squared is 1, 2 squared is 4, 3 squared is 9, ... all the way until whatever n is, assuming it's a pretty large number at some point. And that's what we would have. So once again, let's start laying out what the terms would be. 1 squared is 1, 2 squared is 4, 9, 16, and so on. Okay, and then again, what we're trying to do is figure out if we had like 100 terms or 1,000 terms or some large difficult number to work with, we wouldn't really want to have to write all these down and add them up. So is there some pattern as the sums grow? Is there some way to jump right to an answer? Well, let's find the sums one at a time. Let's see. All right, so the sum of just one term, that would basically just be this so far. That's just 1. The sum of 2 terms, by that point we would have these 2 things so far, so that would be a total of 5 up until this point. And so if you notice, basically this is whatever the previous guy was plus the thing above it, because it's the total sum of all the things up until that point. So at this spot here, we by now would have 14, add on the 16, and now you would have a 30, add the 25, now we would be at 55, and finally add on the 36, and now we're at 91. And obviously you could keep going if you need to. All right, so our goal is, again, if we could find a formula where when you plug in like 5 to it, for instance, it goes straight to 55. When you plug in 6, it goes straight to 91. It just jumps straight to the correct value in that spot. Well, as you can see here, let's assume that the relationship can be determined by some polynomial. Let's assume this is growing by quadratically, cubically, whatever. Let's take a guess that it's doing that, and let's see if that actually checks out. It turns out it does, so it's a good guess. Let's see. If you recall from patterns last year or what we've seen so far in this chapter, if you look at the differences of the terms and watch that how it changes over time, you can make a prediction about what kind of degree this is. So for instance, from here to here, it grows by 4, which really isn't surprising because 4 is how much bigger it got. From 5 to 14, it grows by 9. Again, not really shocking there. So this first row of differences is just the quadratic values from up above. Okay, and so there's nothing consistent yet. I mean, it's growing by quadratics, but this number isn't the same yet, so we have to keep going. Next row of differences, all right, from 4 to 9, it increased by 5. From 9 to 16, it increased by 7. This increased by 9. This increased by 11. Okay, so still not the same. But by the time you get down to this third row here, plus 2 from 5 to 7, plus 2 from 7 to 9, plus 2. At this point, the differences are common. And then what you saw last year, I think, is you only made it as far as quadratics. In that case, they had a common second difference. This is actually, if you look at the rows, the third layer of differences is when it becomes common. And that tells you right off the bat, this must be a third degree. It must be. So we can find some third degree polynomial that fits this thing. We can't do it off the top of our heads, but we can do it somehow. It's possible. So here's the process. Okay. All right. So using this, what's the difference? What's the degree? It's a third degree. Use calculator or any other means. All right. Here's how we do it. All right. We make up some polynomial. We say, all right, the sum of the formulas, or the sum of all the terms, is some cubic thing And if we keep it just open-ended for ourselves, we'll be able to find out what it is. So the sum can be generated by sum cubic, and that's about as open-ended as it gets. You can't make it any more broad than that. Here's the thing. We know a lot of the terms of this, if you will. For instance, we know that when you're only one term in, your sum should be 1. So this formula better have n equals 1, and the answer is 1. We know after 2 terms, the answer is 5. So this better have, if you plug in 2 to n, that produces a 5, and so on. So we actually know what this formula should do. It should produce all the numbers in this list. And as we start laying this out, hopefully you'll see what it'll take to actually solve this thing. All right, so for instance, let's put it all together. If n equals 1, then our formula would be a times 1 to the third, that's 1a, I'll just put a, b times 1 squared, which is just b, c times 1, which is just c, and d times itself, I guess. And then the sum at that point should be 1. All right, so what we did is we plugged in n for 1, and the sum should be. That's one fact about this thing. When n equals 2, plug in 2 for all the n values, n to the third is 8. So at that point we'd have 8a, n squared, so that'd be 4 times b, c times 2, so 2c, d is still all by itself. The sum after 2 terms, again we saw that, was 5. So this should equal 5. Our formula should equal 5 when we plug in 2. All right, so we're starting to build basically a system of equations here. And the thing is we have 4 different letters we're trying to find. Turns out we need 4 equations or else we can't solve this thing. So we just got to keep going. If you put in n equals 3, same kind of thinking, you end up with 27a, you end up with 9b, 3c, and still just a d. At that point on our formula, the sum was up to 14. So that's what this thing should produce. And finally, if we get a 4th value here, after putting in 4, 4 to the third is 64, so that's how many a's there are. There would be 16 b's, there would be 4 c's, just 1 d still, and at that point the sum is supposed to generate a 30. All right, so we have a system. We've practiced a little bit of matrix stuff lately anyway, so if you turn this into a matrix, it's a 4 by 5, plug it in, use the row reduction. Turns out it's a little messy, but what you get is A is 1/3, B is a half, C is 1/6, and D actually ends up being 0. You might get like that E negative 15 kind of stuff. It's a rounding error if that shows up at all, so it should be D equals 0. So apparently the formula is 1/3 n to the third plus 1/2 n squared plus 1/6 n. Apparently that should work, and you can try it with a few terms if you want to. Now, that's usually not how you'll see it listed, because it's kind of annoying that it has all the different fractions there. What you'll usually see people do is they will factor out a 1/6, and they'll factor out an n, since all the terms have at least one n in them. And if you do that, you end up with a 2n squared, you end up with a 3n, and a plus 1. And that actually factors one level further. If you put it all together, here's usually what you'll see. n plus 1, 2n plus 1, all over 6. That's usually the formula you'll see. Okay, and technically you could use the original like this. It's just you'll find this a little bit easier to work with it in this form, especially since n's always a whole number. All right, now one more thing to note here. This only works if you go from 1 until n. And we'll see a couple problems later where that isn't the case, where we start at some other number, and you'll see what we have to do about that. But if you want to find the first however many squared numbers added together, this formula will do that for you. All right, so let's try a few examples. Number 1, find the sum of all 1 to 100 of j squared. Okay, well this is just a direct use of that formula. In this case, 100 is the n. So use the formula. 100 times 100 plus 1, that's 101, times 2n plus 1, that'd be 201, all over 6. That's pretty much it. Just type it in. Obviously, you'll want a calculator for this. When you go and type that in, what you should end up with is 338. 350. So pretty big number, but that's not really surprising because we're adding a lot of squared numbers and they grow pretty big. Okay. Part B, if you looked ahead, is a little bit trickier because this runs into the issue I mentioned before. This one doesn't start at 1. So you kind of can't use the formula exactly as is. You have to think a little bit about it. Here's the deal. If we added up all of the terms from 1 to 71, that would clearly be too much, but at least we have this answer in there, right? That would be somewhere in that number that we're getting. So here's what you have to realize. Well, that is possible. We can do this using the formula because it goes from 1 to something. If only we subtracted off all the extras that we didn't want, that would do the trick, right? So 45 to 71 is all of them, but take away the first 44. that's really the only way to do it with this formula, because this formula relies on using 1 as your bottom number. So you kind of have to do something like this to get the point across. Use the same kind of thinking. The 71 guy, that'd be 71 times 72 times 143 from the 2n plus 1 all over 6. This one would be 44 times 45 times 89, also all over 6. Put that all together. The final answer should be 92,466. All right, so that is how you find sums with quadratics. The same kind of logic is going to apply to this one. I'm going a little bit faster, and actually you'll find this one has a bit of a sneaky shortcut, which is helpful. But same logic, same idea. Let's find some terms, and let's see what we notice. So 1 to the third is just 1. 2 to the third is just 8. 3 to the third, 27. 64. 125. 216. All right, same deal. Let's actually just find the partial sums up until that point. After only one term, you're only at 1. After 2 terms, you're up to 9. After all 3 of these terms, you're up to 36. And so on. Let me just fill in a few more values here. 100, 225, 441. All right, you could use the same process we used above. It'll work every time. And so honestly, if you wanted to find the j to the 4th, j to the 5th, and so on, you could keep doing that, and you'll keep finding more formulas. However, again, I mentioned before, you might notice there's a lucky little break here. You probably recognize at least these 4 numbers, maybe not these 2, but it actually, what you'll notice what the first word does continue to hold. This is 1 squared, this is 3 squared, this is 6 squared, 10 squared, this is actually 15 squared, and this is 21 squared. Okay, so it turns out that if we could find a pattern for 1, 3, 6, 10, and so on, and then just square it, we'd have the answer. I don't know how familiar you are with those numbers. Those are called the triangle numbers. They're actually just the sum of the first n numbers. If you think about it, like, they're called triangle numbers because if you have like these would be a triangle, these would be a triangle, these would be a triangle. If you notice, this had 3 dots, this has 6 dots, this has 10 dots. If it has 1, 2, 3, 4, 5, and so on. So it's really just the sum of 1 to 4 in this case to get to the 10. So if you look at it like this, we have seen that that is the formula for an arithmetic sequence that just goes from like 1 to 100, for instance. And if we just grab that and square it, we're in business. You'll also see it written as n squared, n plus 1 squared, all over 4. If that was too fast, think about it a little more carefully. I'm trying to get through this as fast as I can here, but long story short, that is the formula. And if you use the matrix way of doing it, it works out the same way. So, all right, let's put that down here. N squared, n plus 1 squared, all over 4. Okay, so a little more practice to do here before you start the actual assignment. Here's another one that's kind of weird. You're going to see a few of these popping up. Notice this one has the third power, but it also has a squared in it. So clearly we're going to have to use both formulas somehow. The question is how. Think about this, all right? So if you had, if I just started listing out terms, right? The first term of this sequence would be plug in 1. So I did 1 to the third plus 1 squared. Well, that won't do a whole lot, but that would be the first value you get. Then you'd have 2 to the third plus 2 squared, whatever that is, then, and so on, okay? If you think about it carefully, ... This is a lot of stuff just added together. That's obviously what sigmas do, but there's really nothing stopping you from isolating the parts that you're interested in. So for instance, we have a 1 to the third plus 2 to the third plus 3 to the third, and so on. And then we also have over here 1 squared, 2 squared, 3 squared. We have a sum of cubic stuff, and we also have a sum of squared stuff. If you reorganize it, you can show it. I'm not doing a very good job of writing those 3's, but this is all the cubic stuff and so on. So it turns out you can do all of the stuff you were going to do by just ripping this apart as 2 different sigmas. All right, from 1 to 40 of the third power, and then separately add together 1 to 40 of the squared power. Okay, and if you don't quite buy that, once again, take all of these terms and rewrite them where you have the first 40 third powers and the first 40 second powers together, and you'll see you're really not breaking any rules here. It's totally fine based on the logic that we've seen so far. All right, so use the formulas. There's a third power formula we just figured out, and then there's also the squared one we did earlier. Let's put that all together. So the third power formula would be 40 plus 1 squared, both of those are squared, all over 4. The squared formula would be n plus 1, and 2n plus 1 all over 6. Type those each in, put it all together, you get 694,540. All right, good, that's it. Last one is very similar. I threw a little 4 in there. How does that change things? Once again, think carefully about that. Let's layer out a few terms here. You would have 4 times 1 to the third, plus 4 times 2 to the third, plus 4 times 3 to the third. That's what these terms would turn into, right? Well, they've all got a 4 in them, of course, because it's part of the formula. So if you think about it, there's really nothing stopping you from doing 4 times all of that stuff, right? And this is a sigma notation. So you can actually, using the same kind of logic, just do this kind of thing. Just kind of heads up going into next year. You're going to see a fair amount of this kind of thinking of, oh, just move the number to the front. And if you never stop and think about why it's allowed, you'll totally mess up when it can be done, when it can't be done, and so on. So if you need to, do what I just did. Lay out, okay, there's a 4 in this term, 4 in that term. 4. Oh, of course we can put it to the front. That makes sense, right? So reinvent that logic each time if you need to, just to make sure that it all makes sense to you. But the 4 can just be pulled out to the front, and then we can use the same sort of formula. So this would be the 4 times whatever this thing is, which we can use the formula for. So 15 squared, 16 squared, all over 4. You can actually just reduce the 4s if you want to, or type the whole thing in. It's up to you. Either way, 57,600 would be your answer. So try the assignment. There's a couple pretty tricky ones on there, but just do your best, and then we'll go from there.